Hello everyone. Let's kick things off with a curious puzzle. What do you think happens when you try to calculate 0 raised to the power of 0? Is it just 0? Or maybe 1? Or is it something undefined? Well, welcome to the mysterious and slightly mischievous world of exponential indeterminate forms. Here's the idea. Imagine you've got an expression of the type f of x raised to the power g of x. Normally, powers behave nicely. But in some special cases, things get tricky. Case 1, the base tends to 0 while the exponent also tends to 0. That's the legendary 0 to the power 0 form. Case 2, the base shoots up to infinity while the exponent shrinks towards 0. That's infinity to the power 0. And case 3, the base crawls towards 1 while the exponent explodes to infinity. That's 1 raised to infinity. Now, each of these looks pretty innocent at first sight, but trust me, none of them give you a quick or obvious answer. Depending on the functions involved, these forms might resolve to 1, or 0, or infinity, or even some surprising finite constant. And that's exactly why we call them indeterminate. They don't like to be pinned down until we use the right tools. Now, how do we actually solve these puzzling forms? The trick is to transform them using logarithms. Suppose I define capital F of x equals bracket f of x close bracket raised to the power g of x. To tame this beast, I take natural log. Log of f of x equals g of x times log of f of x. Now here's the magic. If the limit of g of x log f of x equals L, then the limit of capital F of x equals e raised to the power L. That's right, you simply exponentiate the result. So whenever you see 0 to the power 0, infinity to the power 0, or 1 raised to infinity, immediately take logarithms, reduce it to a product, solve the product using tools like L'Hopital's rule, and then exponentiate back. That's the universal trick. Alright friends, let me give you the step-by-step recipe like a cooking manual but for math. Step 1. Identify the form you're dealing with. Is it 0 to the power 0? Is it infinity to the power 0? Or is it 1 raised to infinity? That's your first checkpoint. Step 2. Rewrite the problem in a standard way. Let capital F of x equal f of x raised to the power g of x. That's your base setup. Step 3. Take the natural logarithm of both sides. So, log of f of x equals g of x multiplied by log of f of x. This converts the scary-looking exponent into a product. Step 4. Now simplify that product into a neat quotient form if needed, and then apply L'Hopital's rule or any clever algebraic trick to find the limit. Step 5. Once you've found that limit, let's call it capital L. Just exponentiate. In other words, f of x equals e raised to the power L. That gives you the final answer. So remember this magic chain. Log, then product, then resolve, then exponentiate. If you keep that sequence in your head, you'll never get lost in these exponential mazes. Alright, let's try our first worked example. The limit as x tends to 0 from the positive side of x raised to the power x. At first glance, both base and exponent are shrinking to 0. So this is a 0 to the 0 form. Define f of x equals x raised to the power x. Take log of f of x equals x log x. Now as x tends to 0 plus x tends to 0 and log x tends to minus infinity. So x log x is 0 into infinity, another indeterminate form. Rewrite this as log x divided by 1 over x. Now apply L'Hopital's rule. Derivative of log x is 1 over x. Derivative of 1 over x is minus 1 over x squared. So the fraction becomes 1 over x divided by minus 1 over x squared, which simplifies to minus x. As x tends to 0 plus, minus x tends to 0. Therefore, limit of log f of x equals 0. Exponentiate. F of x tends to e raised to 0 equals 1. And there we have it. The infamous 0 to the 0 form actually evaluates to 1 in this case. Let's also check this result visually. If you plot the graph of y equals x raised to the power x, defined for x greater than 0, you'll see something beautiful. As x approaches 0 from the right, the curve approaches the point 0, 1. The function dips smoothly but never touches 0. Instead, it hovers and glides towards 1. So both the graph and the algebra agree. The limit of x raised to the power x as x tends to 0 plus is indeed 1. Always remember, graphs are like a second opinion from a doctor. They confirm the diagnosis. Now, beyond x raised to the x, there are many other juicy cases. For example, infinity to the power 0. If I take limit as x tends to infinity of x raised to 1 over x, the base explodes to infinity, but the exponent shrinks to 0. Using the log trick, you'll find that the limit is 1. Then there's the iconic 1 raised to infinity form. Consider the limit as x tends to infinity of bracket 1 plus 1 over x close bracket raised to x. This one leads to e, the famous Euler's number, about 2.718. So each case needs careful treatment. Sometimes the result is 1, sometimes it's e, sometimes it's something else entirely. That's why they're indeterminate. Let's do that famous 1 to the infinity case in detail. Take f of x equals bracket 1 plus 1 over x close bracket raised to x. Take log f of x equals x log of bracket 1 plus 1 over x close bracket. As x tends to infinity, log of 1 plus 1 over x behaves like 1 over x. So the product becomes x times 1 over x, which equals 1. Therefore, the limit of log f of x equals 1. Exponentiate limit of f of x equals e raised to 1, which is e. This single example is so powerful it actually defines the number e itself. The same e that appears in compound interest, calculus, probability, and everywhere in advanced math. Isn't it magical that 1 to the infinity turns into Euler's constant? So let's wrap up our journey through exponential indeterminate forms. We studied three main types: 0 to the 0, infinity to the 0, and 1 to the infinity. The universal trick is always the same: take logs, reduce it to a product, simplify using L'Hopital's rule or dominance methods, and then exponentiate back. We solved the classic case limit x to 0 plus of x raised to x equals 1. We discovered the definition of e from limit x to infinity of bracket 1 plus 1 over x close bracket raised to x. And we saw that exponential indeterminate forms are not really mysterious once you have the right tool. So the next time you encounter one of these strange-looking limits, don't panic. Just smile, take logs, and let the math do the work. And that's the foundation of how we handle indeterminate exponential forms. In the next video, we'll continue exploring even more exciting limits and their surprising results.